Hello, everybody. Thanks for joining our July webinar. Today, we're going to talk about building models. I've known of Bob Fassbender for quite a long time. He actually went to school where I went, and I've known this for forever. He didn't know that I knew that, but we both went to University of Wisconsin-Madison. Bob, how long have you been doing? No, you worked for CDS, which was the Train Trace Tech Support Group, which used to be fantastic. I don't know if they still are, but gosh, when I used them, this is before your time, they were the best. They were kick-ass. And anyway, he worked there, and then he started his own company called EnergyModels.com, where they taught people or how to use different types of building software. And they have this online program where you go on, you can buy, courses that are, I don't know if it's a course you can buy. It's a subscription, good for a month, 2 months, 3 months, whatever. And then you can just learn as much as you want about different modeling programs. I've used it a couple of times and I thought it was really helpful. That's all I know about Bob, but he's going to tell us there's a lot about building models that is very, very fascinating. And it's maybe a lot of people haven't really thought about. Building models are great, but they can also be really terrible. And that's what we're going to talk about. Why don't you change the page and actually introduce yourself and then just go right into your webinar. And I'm going to drop my picture. You don't need to look at me anymore. And you said you were going to drop yours as well, but that's up to you what you want to do with that.
Yeah, it's my camera's at a funny angle here. So I'm Bob Fassbender. I founded EnergyModels.com. That's actually not what I primarily do. For the most part, I'm an energy modeler. That's my main source of income. EnergyModels.com was created because there was such a demand for training, and I was traveling and I needed to stop traveling. So that was the gist of that. And then that's been 16 years. And since then, I've started modeling all sorts of different things. So my background is now it's just about 20 years of energy modeling and systems analysis. Thousands of models reviewed, built, supported, calibrated. I know that's hard to believe, but when I was at CDS, it was 20 or 30 a day. And since then, there were some years where that continued privately. My work spans into some interesting things. It's mostly typical things like compliance, incentive programs, early design. One interesting thing where I'll have some information from this that's pertinent to you all is forensic analysis. As an expert witness, I got to work in a project and figure out what went wrong, how it went wrong, and exactly the steps that were taken to make a bunch of mistakes. If we have time, I'll talk about some of the findings and work like that and how that went wrong. But some of that, what I learned there, is implemented in here. I also work in utility procurement, so getting electricity and gas. That is really relevant for performance contracting because when you upgrade a building, it can now qualify for better electricity rates, especially if you saved on demand. And there's also some of this energy efficient stuff causes power factor issues. And so sometimes you decrease your energy consumption and you make your power factor worse and you start paying a penalty for that. There's different ways to fix that. Something I do. So my experience is really unique in terms of what box I fit into because I've been all over the place in models. And I've seen a lot of random models, whether that's someone just calling me for help or sending me a model just randomly, and I get to compare that to real results. I've noticed there's a lot of frequent patterns that you would not expect, and some of them are really expensive for performance contractors. And so rather than talk about the typical modeling for performance contractors things, I'm going to focus on what ends up being really expensive and really expensive to fix. So I'm going to tell some horror stories here, sort of. So before I should say why model. It predicts savings, right? You're committing to a guarantee. You'd want some sort of accuracy there. And the neat part is it's this digital sandbox where you can identify and rank your energy cost measures. And you can't do that any other way besides digitally, unless you had a lab and started building a building. But it supports measurement and verification. Sometimes you can even substitute a model for measurement and verification, and you can get larger loans, better owner confidence. One thing that I have been spending a lot of time the last few years is using it to unlock funding through numerous programs. Name a state, there's a program. There's federal ones, there's local ones, there's city programs. Success in your model is driven by inputs and assumptions. And the one thing that you have to understand, and it took me this is probably the longest thing that it took me to really understand, is most assumptions come from the software before you ever think about them, or if you even think about them at all, it's an assumption built into the software. We'll talk about a few of those. Okay, so to discuss, the main thing that ends up costing people money is the safe calculations, and that cascades into capital expenses, but it also cascades into energy expenses that the model may not track. One thing I'm going to talk about today is it's slightly related to the model, but it's something that I see as a big deal in performance contracting, and that's how some of the modeling inputs interact with the engineering decisions. And then we're going to talk about how to improve the accuracy of your model, because if you create a model and you just run it, I mean, maybe you're within 50% accuracy, maybe you're 3 times off, depending on what you initially selected. So there's 2 themes I want to focus on. One, and I think anyone who's been in the field knows this, design loads are conservative. Equipment is usually oversized. And in the model, that happens before you add a safety factor. And from seeing thousands of models, I can tell you that pretty much everyone adds a safety factor. That's a risk on capital expenditure, but it's also a risk on performance. The next item that you really have to know is that part load is where your contract makes money. That's where the building spends 99 point some% of its time. One thing is for performance contractors, you can actually run a model and overstate your savings unbeknownst to you. If you're running a compliance model, well, unbeknownst to you, you might be understating your savings and say missing out on lead points or missing out on some sort of cash rebate that you could get if you knew the part load operation innards of a model. I'm going to focus on the components that ruin performance that are expensive to fix, as opposed to just talking about oversizing and why that's expensive and it ruins your return on investment. I'm going to talk about things I've seen in the real field, in real models that cause problems. Okay, so why loads are often overstated. This is just like kind of our excuse for why we make mistakes. It's safety, simplicity, liability, code compliance, and then there's industry standards. It's conservative algorithms by nature. More than that, all of the default inputs, so when you fill out a model, you're going to fill out a bunch of defaults, and those are going to be conservative whether you know it or not. So my point here is the risks are not unique to modeling. The whole show is pretty conservative, and it needs to be, because you'd rather be oversized than undersized. But it gets out of hand. People think it's harmless, but it can end up costing you quite a bit, not just in upfront capital. Let's look at how oversizing starts, and I'll try to be 30 seconds here. Basically, it starts with you have schedules. So you put your people, lighting, miscellaneous, infiltration, ventilation, all of those things into the software, and you fill out what they are. And by default, it assumes all of those happen simultaneously. So real simply put, a building has 100 occupants maximum. Well, your model does the math based on your schedules, and it shows there's 250 people in the building. All the lights are on and all the plug loads are on. And the result, because the envelope and the glass all stays the same, and that's factored in, but the net result is you're up 130 to 150% on your load. So one thing you can do about that, there's two ways to enter schedules. Most of the time, the design day ends up being similar to a weekday. You could run a diversity factor. So you have the design day where you show 100% of the people there, and then you could put in 70% as a diversity factor for lighting, for people, miscellaneous loads, etc. And that will account for the fact that people are moving around the building. Okay, there's two components that ruin your contracts, and that's pumps and fans. In this case study that I'll show is more common than you guess. In fact, I think it almost is more common than not. Okay, so let's walk through the math. So there's a building. They made the energy model and they used loads with no diversity, as we said. So they're at 130%. Then they add their 25% safety factor. And then, of course, when they get to the equipment, you pick your equipment and they upsize it by a margin of 20%. So if you add those up, it's not quite as big, but if you multiply them, we're at 195%. Anyone who's been in the field knows that everything tends to be oversized. So it's surprisingly common, and don't worry, it gets much worse. In this case study, we'll look at pumps. Pumps and fans tend to be really significant players in this, and it's not entirely the model. It's this iterative process. Okay, so we have the oversized model, the safety factor, the upsizing. We're double. So double flow, and now we have double velocity. We do our pump laws. Say we have existing pipes, we end up with 8 times the pump power. This is if, and I see this happen. It shouldn't happen, but it does. Add a pump head safety factor, and the result is you spend a lot more on your pump, and it uses 9 to 10 times more energy than it should. The real bad part is that this may not be fixable. The pump minimum flow cannot be fixed by a variable speed drive, and the pump head causes an issue. The model will not catch that. And the model will actually still show savings, and you won't get that savings. And so I'm going to go through the actual data right here. I'll try to be quick about it. So we have the actual model versus the model versus what the right size pump would be. And in green at the bottom, that's the right size pump minimum if they had sized the model correctly. In red, that's what the model predicted. You can see most of the time it spends at minimum stop. In blue is what actually happened. And you can see that the pump spends most of its time at a much higher flow rate than it's supposed to. And they tried to lower the flow rate to the minimum stop, and every time they did, they had pump knocking. And that's because the system was designed for a much higher flow rate than needed. And here's the pump selection. In gray or blue, you can see that the pump is supposed to operate in those areas. And the little red dot at the bottom there, I don't know if it's showing my cursor or not, the little red dot at the bottom is the point that they operated at. So they operated it at the safest and the lowest head that the pump was selected for. And that only got it down to 425 GPM, give or take. So the model assumed, the oversized model assumed 200 GPM. It was really supposed to run at 125 GPM. It ended up running all the time at 425 GPM. And the cost difference on that was about tenfold. Okay, so the model can predict savings, and the building can use more energy. And the reason why is the models automatically assume 20 to 30% no matter what you enter. It doesn't understand the pump head minimum charts for the most part. So when you actually size your pumps, the main thing that you want to check is that you're sizing it according to the modeled load, accounting diversity, things like that. The VFD cannot fix everything. it can only turn down the speed so much. And when we're looking at orders of magnitude of oversizing, you basically end up running a constant volume system. Now, the reason this is really high risk for performance contracts is you can't simply replace the pumps and fans. The duct and pipe configuration is also designed on top of it. And so in this particular case, the pipes needed to be torn out and reinstalled, and it was really expensive.
I just want to add in a little bit there. So you're saying that this performance contractor installed a system based on this model, which they use, which helps size the pump size and stuff like that. And they ended up with then it didn't work. So in reality, they had to go back and change everything out. Is that what you're saying?
That's as much as I can say. Yeah.
Okay, got it. Thank you. Sorry.
Right. And so, can you imagine what that costs versus just getting it done right and installing a 10 horsepower pump instead of, a 100 horsepower pump?
Absolutely.
Okay, so the bottom line on oversizing is it's very common, and compound oversizing is real. You really want to track your assumptions on when something's oversized. Like, okay, we did this, we added a 25% safety factor, because then you hand that off to your engineers and then they add a safety factor, and then they hand it off to someone else and they add a safety factor, and it multiplies. So this impacts your capital expenditure, but also your minimum operating points, and it affects your minimum operating points a lot. So one thing with oversizing, we can basically assume most things are oversized. In the field, when you get the nameplate information and the equipment information, ideally you would find the actual operating information for pumps, fans, cooling equipment, etc. So if a pump is labeled 10 horsepower and there's a meter on it, you could find out, maybe you have to visit it twice, but just check out what the actual kilowatt draw is on it. And from there, you can get an idea of where that pump is running. Because if you pull the pump power and the fan power and you stick that into your model's probably not going to work out, assuming there's a variable speed drive on there. Same for cooling equipment. Most of it's oversized. If you can find out where it's operating, if there's building automation data, that's always really helpful. So oversizing is defined by less than 1% of the hours. It impacts the rest of the year. So what happens the other 99% of the time? That's the next thing you need to know. Okay, so here we have, this is like climate zone 4. It's the number of hours spent in cooling and heating. And it takes a second to understand the chart, but the load increases to the left, and it's the percent of time that you're at high load and low load. And so if you look on the left, it's down to 0%. So in the 0.1% of time, you're at this area where is at your maximum load. And you can see that's actually exponential as we go from right to the left. And that's the actual load. The sizing gets added to that. So the sizing would be actually probably off this chart once you added a safety factor. The rest of the hours, you can see like at 50% of the time, you're at 1/3 of the load for heating and cooling. So if things get stuck, which happens in every building, something gets stuck and it runs at 100%, what happens? And you end up using whatever that component is, you use 5 times more energy at a minimum. And if you have oversized, that multiplies that by even more. Okay, that's just an example of what happens. It makes the energy calculation really easy though. So how much time is spent where if things are working as they should be? So if we have a right size building and it's just on 24/7, just for simplicity, you'll see that it's at its minimum over 50% of the time. And the rest of the time it's above its minimum. If you have a 25% safety factor, you're looking at being at the minimum almost 70% of the time. So it's almost a constant volume system at that point. 80% oversized, depending on if you're doing this by heating or cooling, you're at minimum 90% of the time. So the next thing to understand here, we just talked about the peaks, is so the energy calculation is really easy if you have a constant volume maximum unit. It's just the kilowatts times the hours. The real question is, how does the model calculate the energy in the middle, in the other 99% of the hours? The reason is that part load operation, it will make or break your contract. The model is the best way to mathematically predict it, and it's dominated by unseen defaults. And in fact, most modelers probably go 10 years before they really start to change any of these things. But the term to learn is part load is determined and driven by equipment curves. Equipment curve is unique to each piece of equipment. Each one of them has their own equipment curve. Some of them have multiples, and it changes by brand and by controls, the number of factors. And those are in all of the defaults that you don't realize you're setting. I'm just going to go over an example one. Okay, so this is the standard curve for a 90.1 fan. This is also important for modeling and for getting the savings that, or predicting the savings that you think you'd get. So equipment curve is basically a set of multipliers. If this was a 100 kilowatt fan, we would look at the 1 in the corner, in the lower right, and that's the part load is 1, and the peak power ratio would be a 1. So at full power, it's at 100 kilowatts. It's a big fan. But if we looked at 0.5 and we followed the curve, we're looking at 0.3. And so you cut off half the load, you'd be at about 30% of the power. That's actually a pretty conservative curve because fans unload typically a lot better than that, which we'll get to. This is just the mathematical function. So it's a function of the load, and that makes the multiplier times the peak kilowatts. For cooling equipment, it's actually a lot more complicated than that. There's a bunch of multipliers. I won't get into that detail. I'll just show you an example. Okay, so the most important curve, and you don't necessarily have to decide on this curve, but it's good to know. Sometimes I plot it out because the highest impact curve that you'll have in the model is the cooling part load curve. Here's a default. I'm going to show you what this one ran. And this was someone's default. They were estimating their savings, high efficiency chiller. I looked at the actual curve. Let's see here. The shaded area is the amount of time it's spent within the curve. And anyway, the two multipliers here, if you take the time to go through this, which we won't, it ended up using 50% of the energy that the model said that it would initially. And I guess if you're a performance contractor and now you predict that and then the building outperforms what you expected, that's great. But if you're trying to get money for your model and you're trying to show that it shows savings, that's terrible. And so the bottom line here is curve 1 in green and curve 2 in red. The red curve improved the chiller energy by 50%, a net 8% on the project. And that's something that people don't even see. And pretty much every piece of equipment has that going on in the background. Okay, so when you use the default curves, you can miss the savings. Again, as a performance contractor, well, then the model, or then the actual building outperforms your model, and that's all good. But it doesn't capture the static. It doesn't capture the static or the head as we discussed. So small differences in the curve make a big change. So this is the same for pumps or fans. This is a slight adjustment to that 90.1 fan curve. It's if you're modeling static reset or you're running static reset controls. This fan used almost half as much energy, the one in green, as the one in red. I want to get to something else here, but Knowing that the equipment curves are there, that they dominate the energy picture, and they define your net consumption is something that you really just have to know. You don't know you don't necessarily have to be able to do it, but you have to know that it's an option. Recently in ASHRAE, they started defining the unloading curves. It used to be undefined and people could game models that way. Here's something that should matter to everyone, and I bet some of you are aware of this. Most models and most assumptions assume a 30% VAV minimum. If you go in the field and you measure, you'll find that many boxes never reach down to 30% minimum because of the oversized static or oversized airflow, or the box is jammed shut open with a screwdriver. And when the VAV box is higher than its minimum, that causes energy use on three different ways. So it's a huge option for a performance contractor to come in and fix, but you have to get it right. So higher flow, more fan energy, obviously. More flow, it's going through a cooling coil first, and so it's more cooling. And then since it's more cooling, and most of the time we're at part load, there's more reheat. So really, usually a place to save energy in an existing building is checking the VAV box minimums. And then when you're redesigning a building, you want to make sure that the box can operate as low as it safely can, because you're going to save energy on three different ways that by keeping it at its lowest feasible airflow. Just one thing in terms of the model, sometimes you can change it to CFM per square foot, because many VAV boxes can go below 30%. And so that's just one input, if you're familiar with modeling, that you can enter. All right, so let's discuss, rather than the model detailed calculations, how to get the most value out of a model. So the first thing that I recommend is just even a rough calibration, just changing inputs so that it somewhat matches the actual utilities, because then anything that you do will give you a rough order of magnitude. Sometimes you look at a model and it's using 3 times more energy, or it's using 1/3 as much energy as the building. That can just start by checking the wrong box when you started building the model. If you want to get specific, there's ASHRAE Guideline 14 as a reference framework. Unless you have to model ASHRAE 14, I would use it as a guideline and not actually stick to it. Many times in my scenarios, I have to meet that, and it's a pretty tight framework. The goal is a model that you're willing to guarantee against, and so here's a picture of one that's passing ASHRAE Guideline 14. You can see it's not exactly a match, but then they do this is my spreadsheet, but there's a statistical regression, CV, R squared, NBMBE, and those all have to be within certain thresholds. And you can see the thresholds are pretty tight from the graphs, but they are not perfect. To get the most value, I don't think it has to be anywhere near that perfect, but within like 10% on the year, a month within 20%, the shape should look somewhat similar. So in the gas, where it has that little like dip in February, I would say if you had a model that was close to that, it would not need to show that dip. Okay, so before you calibrate, or if you're having someone calibrate your model, it is not a substitute for sub-meter data. It's still the best way to improve accuracy. And there is something that's probably somewhat interesting on here. A few things are interchangeable. So you could make a mistake on one, like LPD or plug loads. You can mistake those and it really wouldn't impact your net results. Ventilation and infiltration are sometimes interchangeable. You really want to know what matters for your energy cost measures. So if you're doing an energy recovery unit, you probably want to make sure that your ventilation number is correct and running the correct number of hours. In that case, you would not want to substitute infiltration for ventilation, because it would ruin your energy cost measure. So here's an example of a model that just was run and compared to the utility bills. What you calibrate is you build the building as it is and you try to calibrate that to the utility bills. Then you run your ECMs because that gives you an accurate payback. The main thing here is you focus on winter for summer. In this case, we have electric and gas. And I don't know anyone's experience with modeling here if they could guess what was wrong. But one thing you do not want to do is you do not want to start changing the schedules month by month to fix it, because that's not the problem. You want to get the shape as close as possible using standard assumptions, actually using as few inputs as you can, and get those to match closely. And then sometimes you have to calibrate a month. Anyway, in this case, I don't know. See, I look at this and it was pretty obvious to me that there was a ventilation shortage in the model and that something was ventilating a lot more than it should. What gave that away to me was that, well, there was electric heating and gas heating, and you can see that winter has a bigger gap than summer. And there was a few other things that fell in line with that, but that was the first thing that tipped me off. Usually there's an outlier. And so anyone who calibrates buildings, outliers are really annoying because you frequently have to customize something specific to that month. It's often an indication of a special event or an outage. Sometimes you can ignore these, but what this is relevant to performance contractors, because if you don't have records, the outlier itself is information. It gives you an idea on something that you can fix. Why did this happen? When did this happen for 2 months of the year where it used 4 times more energy than it should have? This is where you find an ECM that nobody else scoped. And running the model, so having the model built, I was actually able to run a couple of hypotheses here. And I guessed it, I think I guessed it my first try, was that I was looking at a system and I'm like, I bet they turned this system on. It was a town hall. And so I was like, I bet they turned it on for the elections and they forgot to turn it off. And so I ran that at 100% for a month. And sure enough, it matched almost perfectly. And then they must have turned it off sometime in late December. That was not in the records, but it was just a guess. But since it worked out perfect, I was like, well, maybe the building automation system should talk to this unit, and that could save them, thousands of dollars just off of that happening again alone. And so, if you're not going to calibrate, it's still useful to look at the utility bills to see when the spikes are, because that will give you an idea of what you can fix. I guess if you're not looking at the utility bills, you're probably not going to have a very good contract. But in any case, in terms of modeling, it gives you some options to test if there's no information. One other calibration detail that performance contractors should look at is look at demand first and then consumption second. So if you can look at demand month to month to month, specifically electric demand, that can actually help you identify schedules. It can also, you can find other things that are probably happening wrong with the model just by if there's an outlier in a certain month. Again, it's probably an opportunity to save quite a bit of money. But in terms of for the model, calibrating demand helps you define better schedules, or you can find if there's a big peak during the day where everything's on at once. Different ways to do that. So the one bonus that you get from a calibrated model is you can forecast the new demand after you update the building, the demand and consumption. It is not going to be perfect. I would assume the same statistical variation that you have in the initial set of bills, but I would assume that the amount of variation shrinks by however much you manage to shrink the demand. The goal here is that you can end up negotiating better rates, and that's additional way that you can save on your contract. Okay, so I'm going to get to a little checklist for the field in a minute, but the overall pattern here is you run the model and oversizing stacks into modeling, and then it goes into engineering and back into the model. The equipment size is a lot bigger than the load calculations as a result of the previous bullet point there. We want to check the nameplate flow versus minimum flow if we can. And the biggest takeaway from all of that is that you want to document oversizing and upsizing assumptions at every step. If you added a safety factor and it pushed you into the next size category of an item, you should have that documented. Be like, well, we oversized this by 15%, and now it's 3% over the size of this. Maybe you don't want to upsize it, because right sizing saves a ton of energy and it saves a ton of capital cost. I could give probably a 3-hour set of slides on why right sizing saves energy outside of the capital cost. So here's a checklist that some items that you want to verify. There's another slide here. So pumps and fans, you want nameplate power plus what the actual operation is, if you can. A huge one here is to document whether there's 2-way valves or 3-way valves on any piping, because that's going to tell you, it's going to tell you how the pump unloads. Similar thing with fans is if you have static reset. On cooling equipment, you want the type of equipment, and if you can find out how that equipment unloads, because some equipment unloads very well, like certain chillers, and that saves you more energy than the actual kW per ton. Heat rejection equipment, same deal. If it operates in conjunction with the cooling equipment, that's something you want to know. A huge impact that really not necessarily with modeling is the ventilation. If the controls are working, the energy recovery devices are working, economizers are working. If someone jammed a screwdriver into the ventilation damper, those are things that you want to know, because that ends up being a huge amount of energy. And if you run some of this wrong, it can also cost you a lot of energy. So you want the controls to balance. Okay, we talked about nameplate versus the actual CFM. I think a lot of this is redundant. Useful information is building automation data, pump and fan logs. I ran a whole study for someone just using some fan logs, actually pump logs. I was able to run an entire study on the building, figure out the loads from just the pumping data and the temperatures. Building automation systems are probably one of the best ways to pay back, and that's if you can get the scheduled operation to match the actual occupancy without having overrides destroy your operation. Infiltration is unique to every building. You could have 2 people build the exact same building, or the same person build the exact same building twice, and it will have different infiltration just based on how it was exactly installed. And so you can never trust the default on infiltration. Bottom line there is you want to record what you measured and what you assumed. And if you can find some assumptions that you aren't aware that you used, you would also want to record that. All right, I think we got through that in adequate time. I do have another slide if John's interested, but first, my contact information. I'm Bob Fassbender. You can look me up on LinkedIn. Somewhat of a presence there. It's bob@energymodels.com. Again, I run energymodels.com, but what I mostly do is modeling, overflow modeling, model reviews, calibration is something that has been increasingly popular. And then custom training, we have the online training, but there's also the one-on-one training for things like, well, how do I model this unloading curve? And things that, only specific to one project or two projects. The trainings there have some of that, but it's not specific to any piece of equipment. Okay, that takes us to John. Yeah.
Yes, I've got a few questions for you. How do you recommend designers meet peak load without oversizing the equipment?
Well, you're going to oversize it. Okay, that's just a reality, right? But follow the manual J methods if you're familiar with that.
No,
right?
I'm not. What is that? What
I
is
don't
that?
know. It's a whole guide on sizing things. I think that's mostly residential.
It's what designers use. Okay.
Yeah, it's what designers use. It's not. Okay. So you're going to oversize your equipment. It's just going to be oversized. The main thing that what you want to not do for oversizing is whatever calculation you're adding. If it's in a spreadsheet and you have the lights and the people in there, when you're adding up the total size of a system, it should not include every single light bulb on at the same time, unless that's going to be on at the same time. It's like you want to define the maximum amount of people in the building at once. How that's going to look. Is it going to adjust for their ventilation? And then, of course, how much do you want to oversize? Because you're going to want some oversizing in case the building changes in the future. But when it comes to modeling, in terms of modeling, it's really adding some diversity, and that will size it. You can add some diversity to that. So I think the biggest thing is taking a look at what you did and not adding a safety factor, and then handing it off to your engineer and having them add a safety factor. It's like, know your assumptions, maybe plot it out if you have the load, like if you have the load, some software does show you the people load, the lighting load, the plug loads, and you get an idea of that. Okay. If you add up all the people, does that equal, there's something like in some programs that tells you how many people are in there. Is it way more people than the building is? Well, if so, you really don't want to add a safety factor and then hand that off to someone and they size, it depends what you're sizing. Let's say it's fan coil units. Say we're sizing a pump for fan coil units, okay? There are 100 GPM a piece, and there's 100 of them. Some people will say that that's 10,000 GPM, but we know they're not all going to peak at the same time.
Right.
And so we want to account for that diversity across multiple items. You're going to oversize it, but like that is part of the process, but don't keep oversizing it to be safe. And there are standards to follow.
Okay, let's say you're a performance contractor. You go to an existing building. You're looking at a pump. The pump's 100 horsepower, and it's constant volume. Let's just say it's a condenser water pump or something. I don't know. Okay, there's an oversizing. Is oversizing going to be a problem here? I mean, I just assume it's 100 horsepower.
Are you replacing the pump?
No, I don't want to replace the pump. I'm just modeling the system. Is there an oversizing problem here? I'm just modeling what I see. Is 100 horsepower. I have the GPM label. I'm not going to be able to measure the GPM, let's say. I just don't have a flow meter, so I just take the GPM from the label on the pump. Is that a problem to do that?
No.
Okay.
No, I mean, you might want to like figure out what the brake horsepower is on that pump, because it's probably not operating at, that comes out to 74.6 kilowatts, right?
Right.
And you might want to, if you're actually modeling it, figure out what the real brake horsepower is. It'd be great if you had meter access. You probably don't, but you could do a conversion. You could ask
So,
ChatGPT what that is. Rather than me
so
explain it, but
the
it's not a
oversizing,
problem.
this oversizing isn't an issue in this case then.
No, there's nothing you can do about it.
Okay, so what about if I had an air handler, it said it has, it's a, I don't know, I get what they call them, built up air handlers. I don't know. You go and it says on the label, it's, I don't know, 100,000 CFM. We know what the fan motor size is. Is there an oversizing problem there? It's an existing building. I'm not modeling a new facility. I'm modeling an existing building. Is that oversizing problem?
Depends what you're doing with it.
Okay, and so let's say, well, maybe I'm going to convert it to a variable air volume system or something like that.
Yeah. So the problem with the oversizing, if you're going to slap a variable speed drive onto the motor to convert it to VAV, is how slow can it go, and what airflow can we drop it down to?
That's right. That's a huge assumption. Absolutely. That's right. Okay. Another question. So one thing I noticed, and people have been attending all my webinars. They know I talk about this on occasion. There are these DO2 curves of chillers. And the DO2 curves of chillers, as far as I know, and I could be wrong, they're saying, okay, so if the chiller is at, look, I'm retired, so I don't remember everything, but the chiller is at 100% capacity. It's using, this is the kilowatts per ton or something like that. I don't know, or percentage of input capacity. And if it's at 50%, it's using this percentage of input capacity. So we have a curve. And then, but I thought those DO2 curves, when you have different, it's 100% of load or 90%, 80%, those curves are assuming different condenser water temperatures. They're not
well, actually, there's a separate curve.
Water temperature.
There's a separate curve for that.
There should be a separate curve for each different inlet condenser water temperature. But I thought what I saw was that there's just one curve. Here is the curve. No. And they're just assuming that, okay, you're saying that so let's see, inside of the software, like the DO2 software, they right have here. Separate curves based on the different condenser water temperatures. Is that what you're saying?
Yep. Right here, you can see there's a part load ratio. There's a condenser temperature. Right. I called it out specifically. And then there's a capacity curve. There's the capacity changes with temperature. That's super important with heat pumps, by the way, is to get that right. Because if you use the default capacity, it's like DO2 is using really old heat pump data. And your heat pumps are basically garbage when it's 20 degrees Fahrenheit or below, when in reality, the modern heat pumps can run, below 0 Fahrenheit.
Mm-hmm.
And so the capacity shrinks to 0 at like 25 degrees on some of the default curves. So anyway, that's an additional curve. And then all of those numbers tend to multiply by each other to figure out what the actual efficiency is. I've gone through into the hourly inputs and actually done that to see how the curves are.
Oh, I'm sorry.
Yeah, go ahead.
How do you manage calibration with when adjustments to gas heating and electric cooling parameters create competing errors for multi-zone systems? That gets kind of complicated.
I thought it was going to be an easy question, and then it's not.
Yeah, it's so damn specific. Oh my God.
Well, no, because it's like, how am I supposed to know? Because they're competing. Like, obviously, if you crank up the cooling, you crank up the heating in a multiple zone.
I think,
you know what? My answer to that is they should run a CFD analysis and see which one wins. Make a little tornado.
I'm going to try to answer this based on what little I know, and that is try adjusting the CFM. Because the CFM that's actually being done, assuming you didn't measure it, is not what's on the label of the air handler. You only have, and usually people estimate, based on loads, they'll let the software estimate the CFM is, and it's not right. And I find that if the best way to adjust both the heating and gas, or the gas and the electric at the same time, one of the things is you can do CFM, and the other one is outdoor air minimum or outdoor air percents, because those sometimes will adjust. Those two inputs make massive changes to both heating and cooling. It's just an idea from me who's modeled this.
Wait a second. Wait a second. I misunderstood the question. I thought you were saying that there was multi-zone in terms of cooling and heating at the same time.
Let me read it again because I'm not sure. So it says, how do you manage calibration when adjustments to gas heating and electric cooling parameters create competing errors for multi-zone systems?
Wait, electric, what kind of electric? Was it cooling?
Yeah.
Oh, yeah. See, that's where I was like, you're going to make a tornado if you let them compete.
I thought competing errors meant that you, by adjusting one thing, you fix the heating, but now the cooling's way off. Now you adjust the cooling, and now the heating's way off. And so there are some parameters in your model that'll affect both. Oh, another one.
Yeah. Oh, yes. Okay. I was thinking he was saying simultaneous heating and cooling, because that could be very difficult. If you're saying on one season versus the other, yes, there are some that will make one go up and some that will make the other one go down. And so, for example, if you raise your plug loads, cooling goes up, heating goes down.
Yes. Yeah, and another big input I found that has a huge effect that you wouldn't expect is the deadband. That will increase a lot the heating or cooling. So the deadband, meaning, how often are they going? Well, I'll just leave it at that. The deadband. It depends on the software. My experience is with a program you probably never used called Market Manager, which is long dead. But that was a huge input on affecting the energy savings model.
That's interesting.
Yeah, because the smaller the deadband, the more often the cooling or heating is going to come on, right? So you have a deadband of 1 degree, you're going to have a lot more heating and cooling. You increase your deadband to 5 degrees, a lot less heating and cooling going on, both.
Yeah. Was that in residential software?
No.
Okay. I was thinking the thermal mass would prevent that. But yeah, if you have it at 1 degree, that's going to cycle a lot.
More heating and cooling. I was wondering if you could tell me the state of modeling software today, because we're kind of in a time of change. It's like Trace 700 was the thing we were using at Abraxas, and now they're like not doing support for it anymore at CDS. Is that right? And so they want us to move on to this new software, but the new software had all these bugs I heard, but maybe they're all fixed by now. Can you explain what's going on with software today and what people are using? All of that.
Well, I try not to comment on the state of Trace. Trace 700 was great software, and I'm sad that they ever got rid of it. It was like,
me too.
It's great. It's great software. The new one they're making is they took on something tremendously challenging, and I really stopped checking on its status a long time ago. So without any opinion input, I don't know. Maybe it got better. I've heard that it's gotten better at loads, but as far as what I can personally say, I can't, because I kind of stopped checking on it because I moved on with other things. eQuest is still super popular. It's totally outdated, but it's like a spreadsheet. Like they just don't go out of style. You can use other things for more use. Energy Plus is, of course, gotten big. Really, without being too commercial, IESVE is really dominating in the really high-end space because of what it can do. So if people are doing high-end projects for, try not to name commercial firms, but for high-tier buildings, they're using IESVE. Sometimes Energy Plus. One thing that I want to say is, so I started doing AI integrating with energy modeling, and I really like text-based software for that reason, because you can stick an AI agent on a text-based software, which of course, that's eQuest and Energy Plus. I think actually Trace 3D also runs on the text base. Just while we're at it, not trying to pitch the software or anything, but well, that's one downside. I don't know how IES is going to address that, because I don't believe that all of their stuff is. I think a lot of it's in some sort of private code, and the AI can't edit it.
So some people, yeah. So I was working with Cromer a little bit on using AI, and I think we were using, I don't think it was eQuest, I think it was Energy Plus, and we had some engine that would create models. You tell what the weather station is, you explain, you just type in the stuff. I have a building, it's this many square foot, it's a box, it's 3 stories, and it's got this kind of HVAC. You just write it all out, it'll make a nice model, right? And that's all kind of good, I guess. I mean, I guess that's maybe the equivalent of using a wizard in eQuest and not really knowing what's going on, really. And I guess that works for rough stuff, but you just don't know what, you're talking about oversizing and all this other stuff in the part loads and all that. And you don't know what the model's doing. I guess you can still go, you can have it make the model, and then you can go back. It's like, okay, I got a basic model. Now I'm going to tweak it and make it, fine tune it myself. That's how you would go about doing that. Is that correct?
Yeah, if you wanted to know why it was doing something, you make hourly reports and then back check your math. That's how I would do that. But for what I'm doing with AI is there's, let's say, I'm pretty familiar with the structure of the file structure of something. I don't know. So let's just say I named all of the zones in Energy Plus, and I want to name all of the spaces based on those zones. Well, I could write some code to do that, but I can just tie AI into it and write pseudocode and say, find this zone, and for every zone that has 1 space attached to it, rename the space that this variant of the zone. And I mean, that's a super simple example, but so instead of writing the code to do that, you just ask AI to do it. But I try to write it in as similar to code language as possible. So I'll say or and, use terms that computer code uses, because it's going to rewrite code from that and then process it. So if you have any sort of knowledge of computer code, just like using some sort of and or if phrase, it's going to rewrite the code based on that, and it's going to work a lot faster.
Yes, I found the last model I did was about 3 or 4 months ago, and AI was super helpful, because I forgot a lot of stuff about eQuest, and I would just ask, how do I model this? And sometimes it'd give me, I'd do it and I'd look at it, it's like, oh, that's not right. And you could take, and I'd say, well, something's wrong here. And would say, well, give me I don't remember the file, the INP file or something like that. And I could just upload the file, just copy and paste it in. It would look at, say, oh yeah, look at the zones here, right? See right here, you got this thing that's wrong. It's so neat the way it can read your input files and find the issues. It's like, why do you have your insulation different on this one and everything else? It's like, oh, I don't know. And so, well, let me fix it. Yeah, go ahead, you fix it. And that was really cool.
That's really useful. Cool. It will lie to you.
Yes, it will.
It flat out lies to me, and then it knows who I am, and then it cites my own article to me, and so that drives me nuts.
That's hilarious. Yes, that's great.
I'm like, do you know who wrote that article? And they're like, oh, my bad. And I'm like, and could you at least explain it correctly, because I did not say that. So it will confidently lie to you.
Yes, it will. There's no question about that. No, I mean, it's a very iterative process. Absolutely. You do it and then you look and it's like, well, that don't seem right to me. And then, so it's not something that's going to work for a beginner, that's for sure, because they're not going to know to ask the difficult questions, and they'll just accept all the lies as is.
If you have error messages, though, it's really useful for that, even if you're a beginner.
It's great for that. Great for that. Okay, here's another question. In the past, I've seen people model VAV systems, but they'd only put 1 zone on them. What do you think about that?
trying to think of a polite answer. I think that doesn't make really any sense
I always thought.
because
That's what I always thought. Yes.
because your reheat is going to depend on exactly where the zone is, if it's facing north, if it's facing south, east, west, or both,
Right.
the
Right.
size of it, how much ventilation it has, the
Internal
internal
gains.
loads. You
Yep.
average everything out, boom, you just destroyed the whole purpose of VAV. It's about having small zones. So,
There you go.
uh,
So
but
that
I
was
also
one.
don't like too many zones. You can simplify
No,
it.
absolutely. But I've seen too many models where guys will just do one model. I mean, one zone in a building. I mean, maybe it's a small building, sure, but they won't do enough zones, and it just seems this is silly. Everything's gonna, what's hot on one side, cool on the other side. Oh, they're all gonna mix. We don't need to do any heating or cooling. Everything's just fine. And
Yeah.
that bothers me.
ASHRAE has a definition of thermal zones, and I think their definition is a little strict, but it's not a bad idea. All the walls, all the glazed walls should be facing the same direction. But I'm like, if there's one little window on the other side, just lump it in with the zone. I mean, it's not going to
Mhm.
matter. Now, obviously, they have to be picky for a reason. I'm not criticizing ASHRAE, but I'm saying if you're going to make your own zones, kind of use that definition, but common sense with it.
Yes,
Uh,
use it as a guideline, not a rule. Yep.
yes.
Yep. Good. Do you have anything else? Any last words?
Yeah,
Any
it's
other
kind of weird
questions?
talking into the lidless eye of the camera here. So I don't know if I lost anyone on the modeling. This is all second nature to me. So uh, if there's any other questions, I'd be glad to try to answer them. Did those questions come in from you or?
A couple of them came in from some of the folks, and then I came up with 3 or 4 of them myself.
Oh, okay. So well, I appreciate everyone watching. But we talking with you is nice, John. And so if there's a more specific topic that we have, I can definitely hone in on the energy modeling. This is a very broad topic.
Okay, sounds good. Thank you very much. Take care,
Yeah.
Bob.
Yeah, you
Thanks,
too. Thank
everyone.
you.
See you next month.